Modified Gaussian integral Ix. So this integral is basically kind of the modified form of the well-known Gaussian integral from 0 to infinity of e to the power minus x squared dx. Basically the limits are also changed for the sake of simplicity, and the x is replaced by arcsine x. Everything else is same. And this is the ninth video on this series. Basically I have already solved problems like integral from 0 to infinity of e to the power minus lambda w of x dx whole square dx, and then integral from 0 to infinity of e to the power minus ln of x whole square dx. Similarly, integral from 0 to pi by 2 of e to the power minus sine square x dx, and also other trigonometric stuffs like tan square x dx and many more. So I've already solved 8 such problems, and this is the ninth one. If you want to check those problems, you can check the playlist linked over here or in the description of this video. Now in this video, let's go over this integral. This is a pretty fascinating integral, and the journey will be cool. Now how do we begin solving this problem? Of course you might say that the y equals to arcsine x substitution, and yeah, you are correct. With this substitution we get sine of y is equals to arc x, and that gives us dx equals to cos y dy. Yeah. And for the sake of simplicity, let's just consider the indefinite integral right now. Later on we'll consider definite integral, and this will just be integral of e to the power minus y square, and then dx will be cos y dy. Cos y dy. Now to solve this problem, we can basically change cos y to the powers of e form. We know that e to the power iy is equals to cos y plus I sin y. From this formula, we can derive that cos y is actually e to the power iy plus e to the power minus iy by 2. This is also the complex definition of cos function. Using this, we can get that this integral over here is actually equals to 1 by 2 of e to the power minus y square e to the power y plus e to the power minus y dy. Now let's just merge the powers of e, and then try to simplify the stuffs. This will be e to the power minus, this is y square minus y, yeah, because I have taken minus common. Let's also try to okay, this is iy. I'm sorry for this. This is iy. Yeah, and for the sake of okay, so now fine. This is fine. And like, if you notice something that we will do in next step, plus e to the power minus y square plus iy. Yeah. Now we can try to complete the square over here. That will make things simpler. If you try to complete the square, this will be y square minus iy plus I by 2 whole square. Yeah. Also you have to introduce a minus sign, a minus of this thing, because this was self-introduced, plus e to the power minus of y square plus iy plus I by 2 whole square, and then minus I by 2 whole square dy. Okay, so now we have 1 by 2 integral of this e to the power minus of y minus I by 2 whole square, yeah, and then minus minus plus, and then I square by 4 is minus 1 by 4. Okay, plus e to the power minus of y plus I by 2 whole square, and then minus minus will be plus, and then I square by 4 is minus 1 by 4 dy. Yeah, and now if we take e to the power minus 1 by 4 as common and to the outside, we get e to the power minus 1 by 4 by 2 integral of, this is e to the power minus of y minus y minus I by 2 whole square plus e to the power minus of y plus I by 2 whole square, and then dy. Yeah. Now, how do we deal with this? Okay, so this is basically a standard integral. Yeah. We do have a standard integral, that is integral from 0 to x of e to the power minus t squared dt. This integral is defined as ORF function. Yeah. And from this definition itself, if it's from a to b, yeah, we can basically break this from integral from 0 to b minus integral from 0 to a. So this comes out to be ORF of b minus ORF of a. And that's why we can also define indefinite integral to be ORF of x. Since this holds, we can also define indefinite integral to be ORF function. And we can write it t now and then substitute the different variables that we have. Yeah. So I can say this as ORF of y minus I by 2 plus ORF of y plus I by 2. Yeah. And now what do we have for y? Y is actually sine inverse x. Yeah. Now let's substitute that and we get the answer for the indefinite integral. But we still have to find definite integral. ORF of sine inverse x minus I by 2 plus ORF of sine inverse x plus I by 2. Yeah. Okay, so this is the indefinite integral, and let's check the answer from alpha. Oh wait, I missed something. Very important. So basically this integral is not just ORF of x, this is ORF of x times root pi by 2. I'm sorry, root pi by 2. So please do continue the root pi by 2 everywhere. Root pi by 2, and this also times root pi by 2. I'm really sorry that I missed this. And also this will be multiplied by root pi by 2 for all of this. Also this will be multiplied by root pi by 2. I'm really sorry because I messed this up. To the power minus 1 by 4. Do you understand that? No need to write again. Okay. So this is the indefinite integral, and let's see if the answer is true or not. So root pi by 4 e to the power 1 by 4. Okay, sorry, let's to get this. So e to the power minus 1 by 4 root pi by 4. That's there as well. Root pi to the minus 1 by 4 by 4. Yeah. And then ORF of sine inverse x minus I by 2. ORF of sine inverse x minus I by 2, yeah, that's same thing. And then ORF of sine inverse x plus I by 2. ORF of sine inverse x, sorry, yeah, same thing. So indefinite integral is correct. Now let's try to find the defined integral. And this is from 0 to 1, yeah. Now if you have to find out the definite integral from 0 to 1 of e to the power minus sine inverse x whole square dx. Now if we evaluate this from 0 to 1, what do we get? From 0 to 1. It would have been better if I write over here. So now we have root pi e to the power minus 1 by 4 by 4. Yeah. And then at 1, this is pi by 2. Yeah. So ORF of pi by 2 minus I by 2. Plus ORF of pi by 2 plus I by 2. Yeah. And then we have 0. So minus ORF of minus I by 2, again minus ORF of I by 2. Yeah, sine inverse 0 is 0. Okay, so this is the defined integral. Yeah, and that's the answer. But turns out there are ORF-I and ORF-C functions and not ORF function. So let's try to take the answer in terms of ORF-I and ORF-C. Yeah. So for that, we are going to use some of the properties of R phi, RC, yeah, and such functions. So basically, just like the R function is from 0 to x of e to the power minus t square dt, similarly, RC function of x, okay, RC function of x is from x to infinity of e to the power minus t square dt, and R phi function, this is from 0 to x of e to the power t square dt. Yeah, there's no minus sign. Using these definitions, you can derive that. I again missed something. That something is root pi by 2 over here. I'm really sorry I'm messing this up. Yeah, but I hope you would understand. Did I do any mistake over other places? I think other it's fine. Fine. Okay, and using this, you can basically derive that R of x plus R c of x equals to 1, this formula, and R of ix is equals to I times R phi of x, this formula, and then R of minus x is equals to minus R of x, this formula, and R phi of minus x equals to minus R phi of x, this formula. You can basically derive this to formula from the definitions itself, and the proof is left to the viewers. Yeah. Now with this, we are good to like change this. So basically, we can change these two into RC if we just introduce a 1 over here. Yeah. And over here also, we can change this to R phi by introducing I. Okay, let me show you how. So root pi by e to the power minus 1 by 4 by 4. I can basically write this as R of, let me just say this as minus I 1 by 2 minus I pi by 2. Yeah. And this will be R of, if I take I common, 1 by 2 minus I pi by 2. Yeah. And this one as 1 minus R of minus I by 2, and then 1 minus R of I by 2, and then finally subtract the 2. Okay, so now after this, since R is an R function, R of minus something is minus R of something. Yeah, root pi e to the power minus 1 by 4 by 4, and then we can use this I function to send it to R phi. So minus I R phi of 1 by 2 minus I pi by 2, and this will be plus I R phi of 1 by 2. If I take I common, this will basically be plus, I'm sorry, yeah, plus, okay, yeah, I minus 1 minus plus 1, yeah, okay, fine, and then minus I pi by 2, and then this is ARP C of minus I by 2, and this is also ARP C of I by 2, and then minus 2. Yeah, now let me write let me group these two because they have I in common. We have root pi e to the power minus 1 by 4 by 4, and over here this is ARP C of I by 2 plus ARP C of minus I by 2, and then let me take the I common, and that gives me R phi of 1 by 2 minus I pi by 2, and then also here minus R phi of 1 by 2 plus I pi by 2. Let me also take 2 in this same bracket, so there will be 2i plus 2i, yeah, because I of I is minus 1, that's one. and then this bracket closes, this one also now the big bracket. So this is now the different integral in terms of RC and R phi, and now let's check the answer. So root pi by 4 and fourth root of e, yeah, and then RC of minus I by 2 and RC of I by 2, sorry RC of minus I by 2, RC of I by 2, and the I common, R phi of 1 by 2 minus I pi by 2, R phi of 1 by 2 minus I pi by 2, and then minus R phi of 1 by 2 plus I pi by 2, minus R phi 1 by 2 plus I pi by 2, and then plus 2i, because I is taken the common, so that's why I and 2i will be minus 2 actually. We have also done that, plus 2i. So this is it. Now our both the definite and indefinite integral are according to all from alpha answers, and that means they are correct. We have solved the problem. Then this was a really beautiful problem which involved our phi function and their properties. Yeah. To talk about the flow of the problem, we first made use of substitution. Yeah, and then we used the complex definition of cos y. We computed the square so that we can use the R functions, and then we used R functions, and we then substituted the values, and then we got definite integral. Okay, so we got definite integral over here, and then by substituting values we got the indefinite integral, but we wanted to change that to RC and R phi, so we did that by the necessary means that we had to, and yeah, we got the answer. So this was it, and I do hope that you will check other videos too, and I also think that you enjoyed the video and the solution development and the way we proceeded. Yeah, thanks for watching, and do subscribe if you want to see other videos, and look forward to seeing you in the upcoming videos too.